This is video 268. I'm going to go over Snell's law. We've been talking about refraction, light bending when it goes from one medium to another, and we've been talking about how the index of refraction is a property of the material that is going to tell us how much the light bends. So in this video, we can put all of that together into Snell's law, which relates all of these variables. So Snell's law says that n1 sine of theta 1 equals n2 sine of theta 2. So it allows us to solve for theta 2, which you can see is going to depend on the two indices of refraction, and it's also going to depend on what was the incident angle. So theta 1 is the incident angle, always defined with respect to the normal, and theta 2 is the refracted angle. I made the note. Oh, I didn't make the note. Make sure that these angles here are always with respect to the normal, just like when we talked about the law of reflection. Always draw that perpendicular line and define those angles. So in this video, I'm going to go over just one example. Example number 2 here, it says, what is the index of refraction of this plastic if a ray is refracted as in the figure? So you see the incident light coming in here, entering the plastic and bending. You know that it bends toward the normal, right? Instead of going straight here, it bent this way, which was toward that normal here. And you know that it does that because it's slower in the plastic than it is in air. So we can use Snell's law to figure out the index of refraction. n1 sine of theta 1 equals n2 sine of theta 2. When you use this, just make sure that the index of refraction is related to the angle. So theta 1 is the angle of incidence, which is defined with respect to the normal. So that means that n1 is the index of refraction of air, which is equal to 1. N2 is the index of refraction of the plastic. That's what we're looking for. Theta 2 is the angle of refraction. It is not 55, right? That it's always defined with respect to the normal. So don't just plug and chug the two angles that you're given. Make sure that you look at the correct angles. So angle 1 here is going to be equal to 40 degrees because we do 90 degrees for the right angle minus 50 to get to 40. Likewise, angle 2 here is going to be equal to 35 degrees because we do 90 minus 55 to get 35 degrees. Now we can plug and chug these values into here. We're trying to solve for n2, so n2 is going to be n1 sine of theta 1 divided by sine of theta 2. n1 is 1, so you can just cross it out, and we end up doing sine of 40 degrees divided by sine of 35 degrees. And that will give us an index of refraction of 1.12. So it is indeed higher than air, which is what we expect. I have one more example in this video, but I have already made another video for it, so make sure to attempt this problem and then look at the other video, which I will have linked. This one is a really good problem because you have to use a lot of geometry to figure out the angles. You definitely cannot plug in this angle here into Snell's law because this angle is not defined with respect to the normal of that surface.